Good morning and welcome from sunny Newcastle. My name is Rafal Wrobel and this is presentation on opportunities and challenges of employing heat pipes in thermal management of electrical machines. Well, let's start with a short history of heat pipes. Perkins tube is considered to be a direct predecessor of modern-day two-phase heat pipe system, and on your left there is a Perkins boiler with the Perkins tube, which is an iron tube filled with water, allowing to transfer heat from the furnace to a drum steam. But today we are here to discuss a bit more about heat pipes in electrical machines, and the history of heat pipes in electrical machines is slightly shorter than that of the heat pipes in general, with early examples of employing of heat pipes in thermal management of electrical machines developed in 70s. And here we have a picture from patent. This is Siemens patent, where a heat pipe is introduced in a hollow shaft of the rotor assembly with some feature for extracting the generated heat. We will be coming back to electrical machines and heat pipes in the second part of the presentation, but for now we focus on the heat pipes and the operating principles and the operating limits, materials and manufacturing techniques. So the next slide illustrates a typical heat pipe. So this is here a copper vessel in a form of pipe, filling with working fluid. In this case it's water. On the evaporated side of the heat pipe, water is evaporated and it's transported then to condenser. That is happening due to a pressure difference between the hot and cold portion of the heat pipe. In a condenser, the latent heat is removed, and then the vapor is condensed and returns back via a wick structure. Here capillary pumping is used back to evaporator, and here we have that two-phase cycle between the evaporator and condenser, so changing from liquid to vapor and then from vapor to liquid. It is important to have a sufficient capillary pumping here, and that can be realized by the use of specific wick structures, so grooved mesh sintered. They offer different performance measures. For example, sintered is really good for capillary pumping against gravity, whereas the other ones are really good when it comes to unrestricted or low pressure drop mass flow. When it comes to heat pipe equivalent thermal properties, they are very attractive, from 5,000 to 100,000 watts per meter Kelvin for long heat pipes. When comparing to solid copper, this is relatively a high number. When it comes to size of heat pipes, they can come from micrometers, 2 meters. When it comes to heat removal or thermal management in industrial processes. The next figure illustrates axial heat flux versus temperature. This is a schematic representation for heat pipes to discuss briefly operating limits of heat pipes. So the first on the list is a viscous limit associated with lower operating temperatures, and this is associated with, for example, startup from frozen. The next one is usually present in the startup situation, and it's self-correcting, and it's related to sonic velocity of a vapor, which then chokes the flow. But as I said, it's self-correcting, so we don't need to worry too much about it. And treatment limit is related to droplets of liquid that it's passing in the wick can be torn by the vapor, and then in extreme situation the evaporator can be stuffed from the working fluid and consequently dry out of the heat pipe. So heat pipe really operate as just a shell without phase change effects happening. Capillary limit relates to a type of wick structure. and that needs to be designed to address particular operating conditions. And then boiling limit relates to too much heat or too high temperatures introduced to heat pipe, and consequently boiling of the working fluid and leading again to drying out of the heat pipe. But from the user point of view, what is important here to mention is the orientation of the heat pipe, also acceleration that heat pipe is exposed to, or low gravity operation, for example, for space application, as all those factors affect selection and appropriate selection of a right heat pipe with right wick structure. When it comes to materials used in construction of heat pipes, so usually we consider containers and working fluids. I've listed some of those that might be relevant in the context of electrical machines and power electronics. Copper water seems to be the most popular across applications that we are interested in. So again, electrical machines and power electronics, and also offer the best performance measures. In general, the operating temperature range is much broader for heat pipes, so as low as minus 271 approximately degrees C, as high as 1800 degrees C. It is also important to note that some materials are incompatible. Example here is aluminium water, and that might lead to non-condensable gas generation, corrosion, or material transport, which is not desirable for reliable heat pipe construction. Typical construction or typical application of the heat pipe is shown in the next slide. So on the left we have the usual arrangement: mounting plate, heat pipes, and heat sink. So you might have seen something like that before. This is maybe something less usual, where the heat pipes are embedded in the cold plate, where there are various mounting places for various components, and then that allows to nice heat transport to the periphery of the plate, where there are heatsink features attached to such a plate. It is also possible to fabricate heat pipes to have a different shapes than just the usual pipes. So here we have an example of a vapor chamber or vapor chambers for electronics cooling. The question is where the technology is moving towards. It's been in development for more than 100 years. The manufacturing techniques are well established. While here, additive manufacturing and new materials potentially open unexplored yet avenues when it comes to construction of the heat pipes. Here we have a number of examples illustrating hybrid construction of heat pipes using additive manufacturing. All of those are titanium built examples. Here also there's an example of some of the work that's been done on designing the wick structure and then testing samples for next generation of additively manufacturing heat pipes. And those examples developed and provided to show you by Avid Thermal Division of Boyd Corporation. And here is quite intricate titanium vapor chamber illustrating what is possible in terms of fabrication of a bespoke solution for electronics in particular. When it comes to electrical machines, there are various avenues of introducing heat pipes in thermal management. So this graph schematically illustrates electrical machines and potential location of the heat pipes. So the first on the list is the shaft cooling. Next one is the rotor cooling with radial and axial cooling. Then is a stator both for the winding, for the core pack, and for the end winding region, cavity of the machine, and also bearings. In general, the early work was focused on induction machines, and the power range of the machines analyzed at that time, somewhere between 75 kilowatts up to 150 kilowatts. That early work demonstrated reasonable performance benefits with 20% increase in power density. And one could ask now, so why don't we see heat pipes in electrical machines? As those benefits are very clear of using them in thermal management electrical machines, where there were issues when it comes to cost of implementing heat pipes in electrical machines at that time, and also some associated with reliability of such solutions. There are some examples of commercial use of heat pipes in electrical machines, but just a very few of them. So sooner or later they were removed from the offer. So now we're going to the examples of most recent work, but I couldn't stop myself to show you something that it's one of that early developments to put things a little bit in the context. So this is 1974 work on an induction machine, 12,000 RPM, 7.5 kilowatts, and here the heat pipes are introduced both on the stator winding and a rotor, and the rotor is particularly interesting because here heat pipes work or act as a heat removal feature, but also as a squirrel cage. So the next picture will show you those heat pipes in more detail. So we have a rotor heat pipe, stator heat pipe, and we have a fins on each of those, and the motion of the rotor introduces that air motion among the fins, and then leads to enhanced heat removal from such construction. So following examples are the most recent ones. So here's 2020. It's a permanent magnet machine, 53 kilowatts, 4,000 RPM, where heat pipes are introduced at the end or in the end region of the winding. So the next slide will illustrate that in more detail. So this is a single heat pipe. There are a few of them introduced in the end. So basically heat is generated in the end winding, and then heat pipe then transports that generated heat into the water-cooled housing. On slide just on the right, we have a cross-section through the heat pipe that's been used here. Again, copper water, but interestingly here, this is a hybrid sintered wick with grooves to provide better heat transport. The authors report here reduction in the winding hotspot by 20 degrees C, and also increase in the transient operation. So the transient is now longer, increased by 60%. The next example is a feasibility study of using flat heat pipes, again copper water here with mesh wick to thermal management of a flag switching permanent magnet machine. Here motorette assembly has been used to evaluate various concepts, so transporting heat along heat pipes in the sort of axial direction of the motorette assembly, but also along the circumference. So here authors reported 60% increase in current density as compared with a more conventional heat removal approach, and also possibility for more flexible arrangement when it comes to heat sinking. So the heat sink does not necessarily need to sit on the machine itself. It could be placed somewhere else where it's more conveniently located and easier to remove heat. Another feasibility study illustrated the use of a L-shaped heat pipe that they were retrofitted into conventional induction machine housing with fins, to then illustrate that potentially we can reduce the overall volume of the machine, introduce much smaller fan. Clearly you could replace that existing housing to something much lighter, compact, where the heat pipes allow for that heat transport and effective heat removal from the outer periphery of the machine. And here the authors report 44% improvement in heat removal. Just to note that conventionally machines of this type have some kind of form of wafter attached to the shaft, or for larger machines some external fans, which then lead to a relatively large volume of such a machine construction. So the next example is a 25 kilowatts 100 RPM multi-stage axial flux machine for wind generation application. Here on the figure we have a number of orientations for heat pipes that they were introduced on the winding segments. So you can see here L-shaped heat pipes. And then as you might know, that axial flux machines are particularly difficult when it comes to heat removal, just because of the structure of the machine itself. So there's a sandwich-like structure, which is particularly difficult when it comes to heat removal. And here heat pipes allow to reduce the winding hotspot temperature by 20%, and that led to 11% increase of the generator's output power, And interestingly, that the L-shaped heat pipes that they were placed at the winding periphery, outer periphery here, they were the best in terms of the arrangement and then heat transfer benefit. And the last example here illustrates a hybrid cooling system that combines a conventional water jacket with a heat exchanger with heat pipes, and that heat exchanger here uses fan to remove the heat that is transported from the heat pipes. So that particular concept was developed to reduce energy associated, or energy consumption associated with the heat removal in a vehicle. And depending on the driving cycle, that a combined hybrid system can use, for example, heat pipes when it's needed, not at all time of vehicle operation. So that leads us to some observation and conclusions to be made. So it seems that early research into heat pipes in electrical machines, that 70s and 80s, was somehow more comprehensive than we see now. There are a lot of examples of hardware, a lot of machine built and tested and demonstrated, a lot of work done on the rotational aspects of heat pipes. So heat pipes specifically designed to be placed in the rotor sections or in the rotor assembly, which is not surprising due to the use of induction machines and issues associated with thermal management of the rotor with such construction. When it comes to modern day heat pipe technology, some of the factors like cost and reliability are not an issue anymore in terms of implementation in electrical machines. As an example here are the satellite applications where the heat pipes are designed to continuously operate for 20 years. So some of those issues that they were preventing from successful deployment, commercial deployment of heat pipes in electrical machines are not the case anymore. When it comes future work, we will need to focus on various compatibility issues, electromagnetic, electric, mechanical, thermal, etc. And that is necessary to provide successful integration between the heat pipes and electrical machine. Also, new materials, new fabrication techniques open new avenues for integration as a discrete components, but also creating new active components that already have the heat pipes integrated, for example, when using additive manufacturing. So this concludes my presentation. I hope that you've enjoyed it. If you have any questions, please do contact me, and I look forward to hearing from you. Thank you and enjoy your day.